Thank you. Can everybody hear me okay? Okay, great. Thank you. Okay, so I'm going to talk about two projects in flow-induced noise. The first one is about voice, human voice. And the second one is a cool new facility that they're building in the Aerospace engineering department to do rotor acoustics measurements. Okay, so the first one is this is coming from this project Level Jet Aerodynamics, which just ended this year, started in 2002. And we had quite a large team on this with people at ARL, where we did theory and measurements in life scale models. We had people at Rensselaer who did simulations. We had people at Nebraska who did time resolved measurements in a scale up model. That's a model that Tim Way and I built back at the beginning of this project when we were both at Rutgers University. And then we had our clinical people from Massachusetts General Hospital. And this was funded by NIH. Okay, so we're going to talk about today some of the work that we did at ARL. So just to give you a little overview of the voice problem. The nice thing about the voice problem, if you're working in acoustics, is that it's one of the problems that where we want the sound, we're not trying to get rid of the sound. So that's a nice thing about working on that. So basically what we have here is, this is a really simplified map of the vocal system. So you have airflow from the lungs coming from the left into the trachea, and then that air gets pushed through the vocal folds, through the space called the glottis, and a jet is formed there causing separation. You get an aeroelastic interaction between that flow and the vocal folds, and then the valving of the flow through that glottis then excites the vocal tract, which is a resonator, and we shape the resonator to change the resonance peaks in order to get different vowels. And then the sound is radiated out the mouth. So the sound is produced in the larynx, and it's filtered through the vocal tract, and then it radiates out to the rest of the world through the mouth. So the work inputs here, and what we're talking about in this presentation is we're trying to get a measurement of voice efficiency. So we're interested in identifying the work inputs and the outputs. So the work inputs for this system are the diaphragm, which pushes the air out of the lungs, the posturing of the larynx, so that it's in a position where it can vibrate in the manner that you want, and then in the vocal tract you have articulated posturing, and articulated means the jaws, lips, tongue, and things like that. So that's all inputs. And the outputs basically are the sound exiting from the mouth. So what we want to do is look more closely at the physics here, because clinically voice efficiency is considered to be a good measure of efficacy of treatments. So what what they do is they just take the subglottal pressure, the pressure in the trachea, and look at the sound coming out of the mouth and do a ratio. And the question is that a good enough measure? The other thing is that it doesn't distinguish between what happens when the sound is being produced and the filtering that happens in the vocal tract. So what we'd like to do is pull the whole system apart and look at efficiencies and energy flow in where the source is being produced and also where it's being filtered. So let's look at that. Right, so that's the motivation, which I just said. Okay, so if we just look at the larynx now, and we look at the control volume outlined in blue there, and we look at the integral equation of energy, then we can develop this equation. And I'll just go through the terms really quick, so you see what energy mechanisms, transfer mechanisms there are. So the first term on the left is work done by the acoustics on both sides of the larynx on the flow through the larynx. The second term here in the middle of the room with the box around it is the rate of work done by the flow larynx on the acoustic field in the vocal tract. The next term is the rate of work done vibrating the vocal folds, which you need to do to get voice. The next term on the bottom, the leftmost term on the bottom, is like the box term up above, but now this is the rate of work done on the acoustic field in the trachea. The red term is the loss due to dissipation, and the last term is storage of kinetic energy during this process. So, right. So the other thing we can do is we can look at each of these terms and the sign that they have, and we can determine which are inputs, outputs, and losses. And I've already identified some losses. So you can see that the term, the radiation to the trachea, we consider a loss, even though it's acoustic power, because it's going to the lungs and it's not coming out the mouth. Okay. So the driving pressure work, the box term up in the upper left, that's we consider the input. So, right. So what we do next is we integrate these terms over one cycle, and we end up with, I'm going to do this now. We end up with this equation. So the over bars mean integrating over a cycle. So now everything has units of work or energy, and you can see the similar terms. But now that we have inputs and outputs defined in a simple way, we can now define an efficiency of the larynx, and that's going to be the ratio of the work done in the acoustic field by the laryngeal flow divided by the driving pressure work input. Okay, so we'll talk about estimating these in just a second. So we can do a similar analysis for the vocal tract, and I won't take as long to go through this because it's much simpler. Oh wow! And the Bill Gates seems to have intercepted my talk. So basically, what you have in the vocal tract input is you have the same, the vocal tract energy equation. You have the same input, which is the output from the larynx. You also have feedback from the resonator, which counteracts on that. And then you have dissipation inside the vocal tract. And then you also have radiation out the mouth. So that's the work that the vocal tract acoustic field is doing on the exterior acoustic field. So then when you average these over a cycle, then you end up with these terms, like I said. And the input then would be the same output we had from the larynx. It's being counteracted by the third term, which is the acoustic loading. And then the output is the pressure work on the exterior field. So we can then define the efficiency as the output over the input. And this gives an efficiency for the vocal tract, which we all know how to do because it's a simple acoustics problem. Okay. So in order to estimate these terms in this equation, okay, we didn't derive these equations to solve them. We derive them in order to estimate these different effects. So in order to do this, we need to estimate these variances and covariances between pressure and volume flow, or just volume flow variance. These are difficult things to measure in an acoustic field. So we use an indirect approach. So here's our life scale model. It's got acrylic walls. It's 1 inch square cross section, and We have vocal folds in the middle, as you can see. So we have a trachea and a vocal tract region, and we have pressure transducers to measure the aerodynamic pressure across the vocal fold model. And we have a mouth microphone to measure the radiated sound pressure. We also added 4 more microphones along the duct, and we use the sort of classic approach of Chung and Blazer, which is really old, but it works really well. And what we do is we estimate the reflection coefficient in each part of the duct, okay, using the transfer function between a microphone pair in that part of the duct. And what that does is it allows us to, through some complicated looking equations, to estimate the cross spectra between pressure and volume flow, and then we can integrate those over frequency to get the variances and covariances that we need. This just shows how we made our vocal fold models. We had 3D printed plastic brackets that we molded rubber onto in layers so that we could imitate the structure of the vocal folds. So here's 3 different models that we built. Going from right to left, we have something called the M5 model, which was developed by people at Bowling Green. We added a so-called ligament to our, that was our variation on that. And then finally, we did an elliptical shape, which is more physiologically accurate. And you can see as the vibration patterns that we have, the one on the far right is more physiological than the rest. But the nice thing about this range of models is that you get different degrees of closure, and that affects efficiency. Okay, so here's the same models again, and you can see we're plotting the area during vibration. So it's the mean area are the symbols, and the colors correspond to the models, as you can see. The lines correspond to the max and min areas that you see. And these are plotted versus the driving pressure in the trachea. So using those measurements, we estimated the terms like we talked about. And you can see here, this is for one of the cases, that's the M5L model. You can see these are different terms that we use to estimate the efficiencies. So you can see the laryngeal input is the red. That's obviously the highest. And the output is the blue stars. Okay, so here's some more terms like that. The vocal tract input is the red, so that's the work done in the vocal tract. The blue is the output of the vocal tract, and the black is then what counteracts the red in order to get the total output. Okay, so here's our efficiencies now. The efficiency of the larynx, that's the source efficiency, which is a new thing, like I said. That's the red, and the vocal tract efficiency is very low, as you can see. And so the system efficiency, which is the product of those two, is also quite low. But the nice thing about this decomposition is that now we have a way to look at how the source, the efficiency of the source. So, all right. So, in sum, we did a analysis to identify the different work products that are done in producing voice, and that allowed us to define efficiencies of the source and of the filter, and then we use measurements to estimate these things from our model. Okay, so that's everything I wanted to say about that project. The next project we want to talk about is this exciting facility that they're building in the aerospace department. So this work is led by Mark Miller, who put his name last up there. And he's working with, he has two students, Costa and Eric, in aerospace, and he's working with Eric Greenwood and Jose Palacios. They're all in aerospace engineering. So what they want to do is they want to be able to do testing at different scales, right? Because generally that's what you do when you're making something. And we all know, if you've ever done this, that aerodynamic and especially acoustic results vary a lot with scale. So if you can do testing in one facility that covers all those things, you can do a great deal of benefit. So, right. So what they're trying to do is look at turbine and rotor noise and aerodynamic performance, and they're especially trying to go after multi-rotor, multi-configuration kind of setups. And right, so they're going to do that in the compressed air wind tunnel, which is what they're building. And if you haven't had a chance to see that, you should. It's a very impressive facility out by the airport, or at the airport in a hangar. So let's talk about the facility itself. So you can see this is basically a giant pressure vessel, right? That they push air through. And so the nice thing about it is that right now they can take it up to 500 PSI. That's what they're shooting for. And so they can get very large increase in density, 30 more times. And as you can see with the Reynolds number there, that's generally what you want to match for scale testing. And so that means you can get a 34 times increase in the Reynolds number. The cool thing about this also for acoustic testing especially is that the Mach number doesn't change much when you increase the pressure. It's a much stronger function of temperature. So, one of the things that they're doing right now is they're looking at rotor performance inside the large chamber there right now. And one of the problems that they're trying to address right now is that they want to do acoustic measurements in this high pressure facility, and they need to calibrate the microphones in that environment. So they developed their own piston phone that's on the lower left there in order to do these calibrations at high pressure. So I guess the last thing that they want to do is characterize. They want to treat the walls of the chamber so that they can reduce acoustic reflections. Okay, so right. So like I said, I think this is a really cool facility, and if you haven't had a chance to see it, you should. So I'll stop there. Any questions?
Hi, I just had a quick question regarding that vocal fold experiment.
Yeah.
I was just curious when you're modeling the vocal tract, you have the nasal cavity there as well. Does that play any difference? Or is that a cause that needs to be factored into the experiment?
If you want to be anatomically and physiologically correct, yes. Not all sounds actually use the nasal tract.
Right.
So generally your velum, which is the flap between the two tracts, closes for almost every sound you make, except for ones when your mouth is closed, like or things like that. So
okay, thank you.
That's a good question. Yeah. Yeah, question over here.
So you said that we should go see this facility if we haven't. So while I'm here all week until Friday, is there any opportunity that we can go see it? Because we'll arrange
Yeah,
that. So
guy to talk to is Mark Miller. He's back in the back there. So yeah,
okay,
yeah, he lives here. So
I'll get with you. I'd like to see it.
anything else? All right. Well, thanks very much.
Okay, thank you, Mike. Our next speaker is a government liaison from NASA's Commercial Supersonic Technology Project. Will Doebler, also a PSU grad, as I understand. So welcome.
All right. Thanks for having me. I'm Will Doebler from NASA Langley Research Center. I'm really happy to be here. We're recruiting students, so I hope that some of you will come talk to me after this if you're interested in what I have to share. All right. Nice.
There you go.
Thank you. Maybe we can make this a little bigger too.
Got the clicker up
Yep. I'll set. All right. So yeah, a lot of these slides were made by a lot of my colleagues. So if you don't mind, I've got my notes here. And my talk's broken into my background because that kind of interested me as when I was a student, seeing how people get to the careers that they are. And then we'll go into the acoustics at NASA and some of our opportunities for students and graduates. And then finally, I'll give the outline of NASA's Quest mission, which is its goal is to help enable supersonic transport for civilians across the world. So starting with my background, my title is a research aerospace engineer at NASA Langley Research Center in Hampton, Virginia. And I do work with sonic booms. And I'm also currently working on my PhD in acoustics from Penn State using NASA's advanced degree program. And Dr. Sparrow is my advisor. I worked there for about 4 years. And then recently I've started a full remote work position from Minnesota. Before that, I was at Penn State getting my master's degree. And I worked on the FAA Ascent program. And I got an email blast from NASA that was outlining a fellowship opportunity. And I thought, hey, what the heck, why not apply? And got to spend the summer at NASA Langley with that program. And that sort of introduced me to the managers and the colleagues, and I really liked it. And so that also, Dr. Sparrow hooked me up with going out to the field to measure some sonic booms at NASA Langley. Or sorry, at NASA Armstrong. And so here's that picture, my first NASA photo. Me with my eyes closed out in the desert. We're out there recording sonic booms at the hottest part of the day to try to understand the effects of turbulence on N-wave type sonic booms. These aircraft research opportunities got me interested in all things aviation. And so did you know that you can take flight lessons just up the road here at University Park Airport? So I got my private pilot license to try to understand more of the jargon, and if that's of interest to you, go check that out. Before that, I was a summer intern at a naval base in California working on automatic speech recognition performance. And before that, I was working at Gustavus Adolphus College on my bachelor's in physics, where I got to do some ultrasound research and worked in an ion trapping lab. But a lot of my time was spent playing French horn. And that sort of musical aspect got me into the acoustic side of things. So enough about me. Let's go into our acoustics at NASA. I know what you're probably thinking, well, NASA's typically associated with space research, and there's not a whole lot of sound in space. But NASA's broken into 5 research mission directorates. I'm in the Aeronautics Research Mission Directorate. There's also science, space technology, space operations, and our exploration systems development. So the aeronautics side of things is the terrestrial research group, and we work on reducing the noise from aircraft. NASA Langley is located in Hampton, Virginia, and there's also lots of NASA locations around the country. So there's space flight facilities, there's assembly facilities, and then there's these research facilities. And my team works with people from all over the country. We have our people local at NASA Langley, but then we also have, we regularly work with colleagues from California and Ames and Armstrong, and then sometimes colleagues in Glen in Ohio. At NASA Langley, the acoustics group is broken into 2 branches. They are the structural acoustics branch and the aeroacoustics branch, and I am in the structural acoustics branch. So the structural acoustics branch's goal is to understand and mitigate the impact of noise on people and structures, and its core research goals are through psychoacoustics, sound structure interactions, oralization, and noise control technologies. And the psychoacoustics is, of course, the human response to sound. So we are measuring annoyance to sonic booms primarily. We have one facility called the Interior Effects Room, which is essentially an instrumented living room where participants are exposed to sonic boom noise through a large loudspeaker array of over 30 loudspeakers. And they respond to surveys from in that facility. We also have a team working on oralization, so they create realistic aircraft sounds, and then those sounds are played back in our exterior effects room, which is sort of an auditorium where people can listen to these various oralized sounds of either measured aircraft or simulated aircraft that don't exist yet. And a large area of research in that team is what we're recruiting for. So this is understanding the noise of future smaller rotorcraft, personal rotorcraft. We also have teams working on sound structure interaction. So you can see there on the bottom left, there's a helicopter nacelle, helicopter body, and then we have a couple of rotors that, and they're predicting the noise on the surface of that helicopter. And then we also have a team working on liners. So in the inside of a jet engine nacelle, there's these acoustic liners that absorb sound, and we have a big team working on that. A lot of the products and research they've been doing have been adapted for technology that's currently flying today in our jet and lots of jet engines. And they do research in our liner technology facility, which is a wind tunnel where they can input their various liner tech and understand how those liners absorb the sound. So for the aeroacoustics branch, which is our sister branch, they aim to understand and accurately predict the noise from any air vehicle configuration, as well as define and demonstrate concepts for air vehicle noise reduction. They do, they have 6 expertise areas, from source noise, subsystem measurements, full vehicle systems, source predictions, system noise, and propulsion airframe acoustics. And our researchers work in several wind tunnels, measuring noise from various propellers. And they also get to take their mobile acoustics facility, which is this trailer on the bottom right here, out into the field and record sounds from helicopter flyovers and other sources. Then they use that to create these source noise predictions services that you can see on the bottom left. So between the two branches at NASA Langley, I'm sure there's something that matches your expertise and your interest. We also have several opportunities for students and graduates. The two main websites you should check out are the intern.nasa.gov and the usajobs.gov sites. The intern site has postings for internships, which take place during 3 different sessions. And the let's see, the fall session, or there's the spring session has a deadline coming up in early November. So definitely check that out soon if that's something that's of interest to you. We have good fellowship opportunities. In 2016, they paid out $50K for master's students and $55K for PhD per year. So that was pretty good in 2016. And then our Pathways program is also a really good opportunity for you to get your foot in the door. So this program is you are continuing to work on your master's or PhD, but you spend 16 weeks on site at NASA. And after you complete your degree, you're eligible for immediate conversion to become a employee at NASA. So our civil servant positions are sort of what we're recruiting for today. We're going to have a couple of those probably opening up in around the end of the year. And we have the starting salaries are $66K for masters or bachelors with 1 year's experience and $80K for PhD students, plus there's an annual bonus. There's good work-life balance support in the federal government, so you get your 13 paid days time off per year, 10 federal holidays, 13 days paid sick leave. And there's also recent developments in the parental leave, so both parents can take 12 weeks paid parental leave. You got your federal health and life insurance and 5% retirement matching plus your lifelong pension. We offer flexible work hours, telework arrangements, and you even get to come to cool conferences like this every once in a while. And another important program is after a year, you're eligible as a employee to apply for the advanced degree program. So if you want to continue earning your PhD or even additional master's degree programs, NASA will pay for you to do that. So what do these opportunities at NASA look like? Maybe you'll spend the day hanging out in our 747 simulators or X-59 simulator. Maybe you'll get to go out to the gantry and check out where the Apollo astronauts trained. And that facility is this towering structure that's now used for measuring they're like crash tests from aircraft and spacecraft. Maybe you'll get to spend some time in our wind tunnels. You might get to instrument them with vibrometers. And if psychoacoustics is up your alley, you'll get to spend some time in our world-class facilities to explore that. We also offer virtual and hybrid opportunities, especially for the interns. So if you can't make it out to Virginia, maybe there's still something you could find. All right, so moving on to what I'm working on, the NASA Quest mission. Starting off with some supersonic flight history. Supersonic flight has been around for more than 75 years. And during the 1960s, these aircraft were flown over a couple communities, producing their loud sonic booms in order to see what the public's perception of them would be. And they were finally, it was shown that the sonic booms from these aircrafts were too loud and annoying in order for a commercial supersonic flight to happen, at least over land. So in 1973, the supersonic speed limit was put in place over the land portions of the US and across the world, but you could still fly supersonic over water, which is what the Concorde did up until 2003. And so since then, there's not been a civil supersonic transportation option, but recent advancements in aircraft shaping technology and renewed market interest in high-speed transport has come into light. And so in 2003, the first experiment showing that sonic booms can be shaped to be quieter was completed by a DARPA NASA program. And our NASA Quest mission is, its goal is to collect human perceptual response data of a shaped sonic boom in order to help inform regulators make a decision whether or not supersonic flight should be legal again. So NASA's vision for supersonic flight is to make the civilian supersonic flight possible for people like you and me to get to either side of the country or all over the world faster. The typical thing people quote is that it takes you from New York to LA in half the time that it currently takes. So you can have business meetings in the morning and be home with your family in the evening. There's several barriers. The primary one is the noise issue, but these supersonic aircraft must also be efficient, affordable, and environmentally friendly. Like I said, there's the main barrier is this noise issue. So we need to create these new standards in order to allow for companies to build aircraft and understand how loud they're allowed to be in order to fly supersonic over land. The new regulations have to replace current prohibitions, and we currently have no relevant data on this new noise source, this low boom signal from the supersonic aircraft. And then we also need to get international support because the biggest speed up, I guess, is when you can fly anywhere in the world. So you want to have the longest possible routes, and that standard must be accepted internationally. So NASA's Quest mission then is to help enable these new regulations to be codified. Essentially, we're collecting the data to help the regulators do that. And our NASA Quest mission is broken into 3 phases. The first is the aircraft development. So that top photo is the X-59 being built by Lockheed Martin in Palmdale, California. And phase 1 also includes building the aircraft, making sure that it's safe to fly, and then also we have our preparations for the future community tests. After the aircraft's assembled and is proven safe to fly, we move on to phase 2, which is the acoustic validation portion. And the goal of that is to make sure that the X-59's low boom is what we expect, the loudness is correct, and we can sort of understand how to fly the X-59 in a way to create a range of noise exposures, known noise exposures for our future community tests. Then in phase 3, we begin our community response testing. So for this, the X-59 will be flown over communities, up to 5 communities across the US. And people from these communities will be recruited to respond to surveys outlining how they perceive the booms as either annoying or acceptable. And so then that leads us to what does the X-59 aircraft actually look like? So our requirements for the X-59, essentially we needed to create a cost-effective aircraft that can produce acoustic signals that replicate those of larger supersonic transports. And it has to do this using normal flight maneuvers. It's going to fly at Mach 1.4 around 55,000 feet. It's about 100 feet long. And this aircraft only has a single pilot, single seat. But our lab tests have shown that despite the size of the aircraft, the noise metric is what matters. So it's producing noise metrics that are on par with those larger supersonic aircraft. The design is, there's a totally new airframe, and to reduce cost, again, many of the components are off the shelf. So we have an existing fighter engine And several of the other components have been taken off the shelf to help reduce the cost of the development. So Lockheed Martin is the lead for the manufacturing. NASA's one of the unique features of the aircraft is it has no forward-facing window. So NASA has developed an external vision system that allows the pilot essentially to be looking at a screen through a couple cameras in order to land the aircraft, because the very long nose prevented a forward-facing window. And you can see it's coming together here in the bottom. We just completed ground testing in Texas. I think a couple of months ago, and its first flight is scheduled for early this year. Or this next year, 2023. So how quiet is it designed to be? We use a different decibel scale than you might be used to. So like A-weighted decibels, for example, did not correlate well to the impulsive type noise and the low frequency content of the sonic booms. So we use this perceived level PL metric that was shown to correlate well with human perception of booms. It's a little bit more complicated than like A weighting, which is just a single weighting filter. In PL, the sound's broken into its frequency bands, and then each of the bands is weighted based on its level. Then there's a summation procedure to come up with the final perceived level decibel measurement. So we did a small scale study of different impulsive noises, and that's shown on this thermometer type scale here. You can see the Concorde sonic boom, which was deemed too loud and annoying to be flown over land, is shown around 105 decibels perceived level, which is comparable to nearby thunder or a car door slam inside the car. And these types of sources can be pretty startling and loud. But the X-59 was designed to have a 75 decibel sonic boom, which is shaped sonic boom. They're calling it a sonic thump, and that's comparable to distant thunder or a car door slam down the road. Just to put that perceived level decibel in context with other sounds. Another interesting thing sometimes people don't know is that a sonic boom is produced the entire time as an aircraft is flying supersonically. It's not just a single event when you pass through the speed of sound. So it's dragging this impulsive noise behind it. And it can be up to about 50 miles wide, depending on the atmosphere of the day. So with a 50-mile wide carpet, they call it a carpet, flying hundreds or thousands of miles across large swaths of land that aren't used to transportation noise, you can see how this loud sonic boom could be a problem. You could insonify millions of people very quickly. And so why is NASA ready to move on to these large scale community tests? We started in the lab. We did many of psychoacoustics tests in our interior effects room. And then we moved on to small community tests where we tested out our survey methodology. Then we moved to a larger community test in Galveston, Texas in 2018. All of these are increasing the complexity, the number of people involved in the survey, changing the location where the aircraft is based is a big issue. And then also interfacing with the communities, bringing a new sound source into the communities is a challenge, especially with trying to reduce the bias that informing, the population of these communities. When you go out into the communities, you have the potential for biasing them with your media outreach. So we're trying to take steps to reduce that. So with all these lab tests, risk reduction tests, we think we're about ready to go out into the communities across the US and national scale. And the type of data that we're going to be collecting is shown here for some of our risk reduction tests. The purple is for the large community test, and a smaller community test is green. So on the horizontal axis, you have perceived level, so that's the loudness of the sonic boom. And then on the vertical axis, you have percent of people highly annoyed. So we fit models to these, there's big scatters in these type of social surveys, which is typical, and we try to fit models to the loudness versus annoyance data. You can also see that at about 75 decibels, there is not a huge, it's less than 5% of people highly annoyed. And so that's one of the reasons that the X59 was targeted to achieve a sonic boom of that level. And it's a challenge because it's actually a challenge to model this type of data because there's so few, there were so few observations of high annoyance in our community tests. So it's an interesting modeling challenge while you're also trying to understand where this threshold of onset of annoyance exists. We call that a dose response curve. So the dose response, the dose in this case is the noise, and that axis has some challenges. It's hard to estimate the loudness that a person heard. People are just going to be going about their day in their homes, and we aren't going to be instrumenting their homes. We'll be laying out a sparse ground measurement array of microphones in the communities, which could be about 1,000 square miles is our survey area target. So we need to estimate what each person heard, and we do that by combining our acoustic measurements with physics-based model predictions. And we're going to use a technique that is often used in the atmospheric modeling community, a assimilation technique to combine measurements and simulations. But we need to also address uncertainty and make sure we're accounting for uncertainty in our dose response curve. We also, there's a lot of sensors going to be placed around a large area. So these sensors will be, they won't be attended. They'll record the sonic boom automatically. And we also have issues with signal to noise ratio because the background noise in cities, for example, may bury our sonic boom signal. So we're looking at using a replica correlator to pull out the signal from the noise. The vertical axis also has some key challenges. So we need to make sure that despite only having 5 community tests planned and budgeted for, we want the responses to be nationally representative. And we also need prompt responses. So we decided to use a web-based survey. And so the participants are able to quickly respond to whether or not they heard a sonic boom and if they were annoyed by it throughout the day. There's up to 6 booms per day, and the tests are going to be about a month in each community. So we're also looking at ways to reduce survey fatigue. We need to know where the participants are located when they hear the boom so we can assign them a noise dose. And there's also challenges that we're not able to mask the purpose of the survey because it's a new noise source. So all these smaller community tests that we've done have been helping us understand how to get the survey out into community effectively. We also have one other challenge that these participants respond throughout the entire month. So all of their responses to the sonic boom noise are correlated. And so we have to use statistical models to account for the correlation between annoyance from individual subjects. I think that's most of the hard parts. So I'll move to the summary and then I'll take questions. Our Quest mission will soon be flying the X59 over several communities across the US. We'll be collecting noise dose and perceptual response data to inform potential new supersonic aircraft noise certification standards. We're currently in the planning stage and we're working to solve some of these challenges. And I hope to talk to many of you graduate students and people looking to apply for jobs after this. So check out intern.nasa.gov and usajobs.gov. Thank you.
You mentioned that you guys had flyover oralizations and you were looking at specifically indoor conditions when you were doing the subjective tests. I was wondering what type of attenuation or absorption algorithms you guys had implemented to make it more like the indoor noise versus just external oralizations.
Yeah, that's a good question. So one of our facilities can play back either external measurements or these indoor oralizations. There's a big software suite you can check out. It's the NAF, NASA Oralization Framework, I think it's called. And that has things like effects of the ground impedance, I think small scale turbulence. And I can get some of my colleagues' information to you if you're interested in that sort of thing. The interior effects room, so if you're interested in like oralizing sonic booms from any aircraft, really, the interior effects room itself is built to sort of be a living room. So it actually implements physically the transmission loss and from outdoors to indoors. So we usually play back outdoor signals from sonic booms, and then you can hear them after they've come through the walls of the interior effects room for the indoor portion. Thanks for the question.
Hi, I understand that we hope to have these planes flying commercially eventually, which I assume means we'll have multiple planes flying at the same time. And I'm wondering if there's any concern with overlapping carpets, I think you called them.
Yeah, that's a good question. So there's that perceived level metric that I talked about. That's for like a single event, one sonic boom. And I think it's pretty unlikely that two sonic booms would, overlap on the ground from multiple aircraft. I guess it's possible. But we also talk about a cumulative type metric. And so that's similar to some of the other FAA subsonic noise metrics where you compute, it's like a decibel weighted sum of the single events of the day. It's like a day-night level metric. And so regulators will also be interested in managing the day-night level essentially of sonic boom noise. And that's another goal of the test that I didn't get into, is we want to understand the cumulative dose as well as the single event doses. Thanks for the question. Anyone online? All right.
Thank you, Will. Our next speaker is another government liaison, Anthony Manolo from the Naval Surface Warfare Center Carderock Division. And he'll be talking about what they do at Carderock. So please join me in welcoming Anthony.
All right, so good morning. I think I'm the last one before lunch, so keep that in mind. So as was said, I'm Anthony Bonomo. I'm here on behalf of the Acoustic Signatures Technology Division, which is called Division 7-2, the Naval Surface Warfare Center Carderock Division. That's within the Signatures Department at the Carderock Division. So like Will, I was torn between music and engineering. Undergraduate, I was a jazz studies major and a mechanical engineering major. Someone mentioned to me I could do acoustics, so I was like, that's crazy. I didn't know that was a field I could go into. I then got an internship at Carderock and loved it there so much that I ended up getting a SMART scholarship, which is a fellowship program that's still very much available. And if you have any interest in that or internship opportunities, please talk to me. I went to grad school at UT. I was at the other ARL. Don't hold it against me. But my colleague, Trevor Jerome over there, he's a Penn Stater, and he'd be happy to talk to you as well. Yeah, and Marylou McNamara, she's the division head. She sends her regrets. She was originally going to be giving this presentation, but she's not able to travel. So, all right. Let's see, next slide. There we go. All right. So where are we? So we're the Acoustic Signatures Technology Division, as I said, at Carderock. Our home base is West Bethesda, Maryland. That's just 8 miles outside of the DC city limits. And it's a very nice place to work. I would say that the big selling point, maybe it's a little less of a selling point these days for DC, is that it is the solution to the two-body problem. So if you do acoustics and your partner does something completely different, you can both find opportunities in DC. There's no combination that's not possible. So that's why it's a great place to be, especially if you're dealing with that. And in addition to our home base in West Bethesda, we do a lot of testing at what's called the Acoustic Research Detachment. That's in Bayview, Idaho. It's a beautiful place to visit, and it's probably quite a nice place to live too, I'd imagine, because weather's actually pretty temperate over there. And I'll go over our facilities there a little bit as we progress. So in terms of what we do, so we have about 120 engineers and scientists. I think it's about 1/3 of our employees have a PhD. Another third have a master's degree. That's something that's very strongly encouraged, and a lot of people enter with just a bachelor's degree and then go on to do graduate programs that are sponsored by the DoD. A lot of people do or try to do Penn State distance, either taking courses or actually getting degrees from here. We collaborate quite a bit with Penn State. In fact, some of my most trusted and capable colleagues are at ARL Penn State, and get into that a little bit and how we work with them as I progress here. So a couple of things I wanted to kind of highlight here in terms of our technical capabilities and our facilities. So I'll be going over kind of each of these bullets with subsequent slides. Just wanted to point out though that so the hydroacoustics group and the structural acoustics group, those are kind of our knowledge bases. Those are where our subject matter experts are that support the division. And I'd say the hydroacoustics group is probably most closely affiliated and associated with the work that's been done by the CAV group, the Flow-Induced Vibration group. Structural acoustics is kind of the sister to the structural vibration and acoustics group here. And we also have acoustics materials group that do some metamaterials research. And a big area, of course, everyone is talking about is machine learning and AI. So we have that going on as well. So if you're in those CAV affiliated groups, please talk to me and we can talk about collaboration, or if you're a student, employment opportunities. Something that we are focusing on quite a bit these days is kind of really 2 big projects that take up most of our tasking across the division. The wrapping up the research and development for the Columbia class submarine, which is the future replacement for the Ohio class submarine, which is the nuclear deterrent. So that's we call them boomers, right? And then there's we're starting to ramp up into the replacement for the Virginia class, which is our attack class submarine. So that's the we call that now SSNX. It's unnamed. It'll get some fancy name at some point. So that's most of our tasking. We would do stuff with surface ships as well. And really the main purpose of this of our division is we're kind of the go between cutting edge research and the the fleet. So a lot of the research is funded by Office of Naval Research, a lot of research that gets conducted by graduate students at Penn State. The next step in its journey is to Carderock for prototyping and evaluation. But we do some basic and applied research as well at Carderock. So we're stepping through some of our capabilities now. Big knowledge area for us is hydroacoustics. We are the kind of the Navy's experts when it comes to hydroacoustics, specifically dealing with flow-induced vibration and noise. So a lot of what we do these days are experiments related to that. I'll talk on the next slide about our one of our facilities, the acoustic flow facility. We also do a lot of very high fidelity numerical simulations. So if you have interest in computational fluid dynamics, especially things like large eddy simulations, or do finite element analysis, please talk to me. That's something we're very interested in. So you can see a depiction of a nominal boundary layer over our hull. A lot of the cooler pictures I can't show today, but we do a lot of neat stuff and very, very intensive calculations. We're talking, for finite elements, like hundreds of millions of degrees of freedom, and quite a bit more for CFD type stuff. So one of the first facilities of its kind is this anechoic flow facility. So you've actually seen a couple depictions of these circulating wind tunnels that have anechoic sections. This was probably the first in the world of that type of facility, was at Carderock, and it's still maintained, it's been updated, and it's still very much in use. So it's kind of two purposes, is to assess the flow-induced vibration for various scale models, and also for propeller and propulsor design. So at the Acoustic Research Detachment in Bayview, we have a number of scale models. We call them large scale models because they can be as large as, let's say, quarter scale of the real thing. So kind of the earliest type of testing we did was this type of testing. We call this a pop-up vehicle. You submerge this vehicle and just let it go. It's a very highly instrumented, so you actually get good measurements of how the flow induces vibration on the hull. You can actually have some hydrophones on the range there, so you can actually measure the radiation from the hull as well. But also you get a sense of what's called self noise, how much your sensors on board are picking up the flow noise, and something that's not something you want. So something we do at relatively low cost that can be reconfigured relatively easily, and ARD is a great place to do that. The Lake Pond Array, one of its big selling points is that it's the sound speed stays relatively constant once you get it below a few hundred feet in the lake, which is I think it's one of the deepest lakes in the US, in fact. So all year round, we do testing of these buoyant vehicles, and some other testing I'll be talking about in a bit. So I'm in the structural acoustics branch, so I can talk a lot about this area. We are very much the Navy's experts in this area. We do a lot of collaboration with folks that do similar research at ARL. And we really are the transition partners between what they call science and technology, like the very basic research in this area, to prototyping and coming up with mitigation strategies for controlling and reducing our signature. A lot of what we do these days is based on modeling and simulation, just like in the hydroacoustics group, a lot of finite element modeling as well. We also are the experts that design the tests and help oversee the tests that happen at ARD. So even if you are working in West Bethesda, there's a lot of collaboration and opportunity for travel to the ARD, especially if you're in the structural acoustics group. Trevor's also in that group, and if you want a little more about what we do, I'd be happy to talk to you, after this, or answer any questions afterward. So from the structural acoustics perspective, probably our most important facility at ARD is what's called the ISMS. It's the Intermediate Scale Measurement System. So this is great, and this is very useful for making predictions of how the full-scale platform will perform acoustically, and when it comes to the presence of machines or pumps or treatment strategies on a scale model that is very representative of what's in the fleet. This is also great for model validation and testing of simulation tools, because our models here are very highly instrumented. You get onboard and an array of hydrophones, 158 hydrophones. You get the full 360 azimuthal coverage. So we get the radiated transfer functions, and this is like the first stop. Anytime we want to test a new computational capability, we start with the data that we have over the years from this ISMS facility. Originally, it was actually developed for target strength and scattering. I'll talk about target strength in a little bit, but it's mainly used these days for, there's a source on the platform. We're trying to see how it propagates to the far field. All right, so propulsor acoustics. So at one point, this was part of the structural acoustics branch, but it was split off at some point because it's worthy of its own area. So it actually turns out that there are two design agents for the propulsor for the Navy. So the thing in the back that makes the boat go, which is the Carderock and ARL. And we work very closely with ARL in this area. So our main focus has been on Columbia class lately, and we're transitioning now to this SSNX. And we go all the way from basic research to prototyping and full-scale testing. So the propulsor is unique in that it is one of the areas that is government furnished, which means that the government designs it and actually builds it and delivers it to the boat. So if you work at either ARL or Carderock in this area, you get a direct influence over the design of this system. And obviously, this is something that we want to make sure behaves acoustically the way we want it to behave. So it's very important. So our biggest asset when it comes to propulsor acoustics is what's called the large scale vehicle, or LSV. We're actually on the second iteration of that now, which we call LSV2, or the cutthroat. It's at ARD. It's a semi-autonomous submarine. It's the largest such submarine model in the world, and it's mostly used for propulsor assessments. So after we go through the design cycle, we have our testing and modeling. So we'll do testing in water tunnels, or maybe our anechoic flow facility. We'll do some simulations, and we say these are the designs we like. We actually fabricate the scale models of the propulsor and test them at using the LSV. It's kind of the last stop before we decide whether we like a design or not. And it's really neat. If you actually go to see the LSV deployed, you usually run it at night so that the ambient noise is quite low. And if you're actually in the dock as it's being deployed, if you get the right aspect as you're looking at it, it kind of looks like the real thing, just being deployed. It's really neat experience. So another piece of government, provided technology is the any sort of treatment that gets provided to the hull for acoustic signature mitigation. So our group, the acoustic materials group, is involved in the full shebang. You going all the way from basic research, that involves some metamaterials research, and coordinating research activities that happen at universities and elsewhere, all the way down to delivering and installing on the fleet. So something you see in the graphic here is a new installation technique that was developed that saves time using these so-called super tiles. We're the true experts in this area, and we're definitely looking to grow our capabilities further. Okay, so kind of the opposite coin of the structural acoustics, which is dealing with how sound radiates from a platform, is target strength, which is someone is pinging at you with some sonar, and how does the sound scatter from the platform? And you want to make sure that you control the reflections that come from the interface with acoustic waves that are called active acoustics. So the main activity in this area is maintenance of this what's called the target strength predictive model. So it turns out that target strength experiments are quite costly, even on the scale model. So we have these, we try to strive to develop these physics-based models of the target strength. And We maintain that. Carderock is the main activity there for that effort. So we also have some scale model testing on that ISMS, and that's actually coming back more so because of more stringent requirements for SSNX and some high fidelity simulations as well. So here's a kind of canonical summary in the skipjack, and it's a good representation of the kind of models and the way we take a design like this and we turn it into an assembly of relatively simple shapes, which we have analytical solutions for. Kind of the first step for the TSPM. There's some more sophisticated analysis we can do with some other tools to corroborate that we do have a good prediction of the signature, and then obviously comparison with scale model data. So yeah, I mentioned a few of the scale models already, but we have quite a few more we use across the division in all disciplines, sub-disciplines, I'd say, of acoustics. And so for target strength, we use some of the same scale models we put on the ISMS range, get the scattering strength from the targets. And then also we have representations of scale representations of many of the assets we have in the fleet. And in addition to our model scale testing, we have computational models. And this is a lot of what I spend my time on, is trying to get us to the cutting edge of the modeling and simulation tools. So we are really developing our capabilities in our computational hydroacoustics and computational structural acoustics. So for hydroacoustics, really, it's CFD is the main avenue now. We're looking at that helps us calculate what the forcing function that we apply to our structural acoustics models should be, and also getting a sense of how if you have a disturbance, some unsteady flow, how that actually just directly propagates and as a source of noise. When it comes to computational structural acoustics, we have your finite element, boundary element, and energy methods, and all sorts of other semi-analytical techniques that we use. And more and more these days, we're leveraging these very massive computing systems, these high-performance computing systems. So there's a program called the DoD HPC Modernization Program that across the DoD, we coordinate with all the other branches of the DoD to field these supercomputers. And for some very sensitive stuff we'd like to keep close to the vest, we still use in-house computing clusters. We have one depicted here we call Mach 1. It's relatively new, and we're looking at developing Mach 2 in the future. But that's an interesting system. It's every single one of these the nodes of this system would be what's considered a large memory node on most HPC systems because of the demands of our structural acoustics models in particular. So another area of interest, and more so, is airborne noise. So what happens is you part of the quieting strategy might be that if you have machinery right in a closed space, you want to make sure that the noise doesn't get out right of the submarine, but that means it stays in, right? So you have some habitability concerns. So we needed to get a little more sophisticated in how we do our modeling. So we use kind of two approaches here. One is using this commercial tool Odeon. So if those of you in architectural acoustics, you're probably familiar with that. So we've applied that to the problems of ray tracing when it comes to enclosures on platforms. We also need to understand how much of that sound actually gets out into the far field, and there isn't a commercial tool there. So this is a pretty new development for us. We have something that we call the Carderock Acoustics Ray Tracing Engine, or CART, and it's pretty novel. You're not going to find that anywhere else. Still in active development. We're looking to grow the team that is developing and performing calculations using that tool. We also have acoustic cameras that we use to make assessments of noise sources in situ on trials and in for our scale models. And then lastly here, I'll focus on the big emerging area, which is data science, machine learning, and AI. So the one thing that Carderock has that you can't find anywhere else is we own the signature for the Navy. So all the data that gets collected, not just for acoustics, but across all the signature areas, it's stored at Carderock, it's processed at Carderock. And we have decades and decades of this data, and we have essentially the big data problem, and we're trying to address that with AI ML approaches. Also, we're more and more using these types of techniques in our modeling and simulation tools. There's something that I've been working on recently. It's called surrogate modeling, which is you have those very high fidelity models that take a long time to run. You don't want to be doing that when you're trying to assess many designs. So the idea is you just run a few of these, you train a neural net and say, can it spit out a reasonable approximation of the answer? And we have all this trial data that we can use to benchmark off of as well, from various platforms, those sorts of modifications. So that's a very active area of research at Carderock. And if you have any interest in this, please talk to me. So I'll just stop to say that we are hiring. We have a new nifty email, carderockacoustics@us.navy.mil. So please feel free to reach out there with any questions or if you have any interest in joining our team. I don't have a nice benefits slide like Will had, but I will say that as a federal employee, you get many of the same benefits. In fact, just about all of them that Will talked about are, even though we're in the DC area, it's quite could be an expensive area to live. Our compensation is quite competitive, I would say. So please, if you have any questions or any interest, talk to me or Trevor. We'll be around today and tomorrow. So thanks for your attention. All right, happy to answer any questions. I know it's right before lunch, so it's always tough to get questions.
Hey, Anthony, can you hear me?
Is that someone talking?
Yeah, this is Steve Hamrick. I don't know how my mic's working. Had problems earlier.
Up above, yes.
Yeah, I just want to chime in. I started my career at Carderock back in the late 80s, and it's very, it's like a big campus. There's all these different groups, and like Anthony said, there's so many opportunities, people to work with. It's a great place to start if you're a graduate student. Lots of possibilities are endless. You can really do anything there that you want. So I'd highly recommend it.
Yeah, I appreciate that, Steve. And yeah, we have a lot of people who've kind of, we cross-pollinate with ARL quite a bit. They go back and forth, and they're interested in the research opportunities you have here, but for some reason, your partner drags you, to DC. You know where to find us. We're the right place for you. All right. Well, thanks for your time.
Okay, well, just a couple announcements before lunch. For those of you here in the building, lunch will be out the door and to the right, over at Alumni Hall. Hope to see you all there. Sorry for those online, we can't offer you any lunch. You'll have to find that on your own. After lunch, we'll be doing the student poster previews. So the students who have posters, please make sure you're here a few minutes early so we can go over what you'll be doing. So come in about 1 o'clock and we can chat. Students who are here, raise your hands so that people in the room can see who are students. So if you're looking to hire people, those are the people you want to sit with at lunch. So who's looking to hire? Either immediately or in the next year or two. Okay, so students, see these people, sit with them at lunch. Okay, so everyone enjoy lunch. We'll be back here, start up around 1:15. So about 1 o'clock, start wandering back in. Thanks.